Now let's consider what happens when we have the source of EMF connected to a circuit, unlike the previous example where there was nothing connected. Now we have an external connection. Now I'm kind of generalizing this. It may look like a short circuit or just a conductor across there, but there really is a resistance R here, so I'll put this resistor symbol next to it to help you realize that whatever's hooked to across the battery has got some resistance. Let's consider it uniformly distributed resistance just for perhaps sake of clarity, but it doesn't really matter. Now we have this non-electrostatic electric field, and that is a constant of the battery, and it separates charges. Now those charges have a path through which to flow, so some of the charges leave A and go to B, and that causes a reduction in the charge separation, reducing the electric field. And so now the electric field, the electrostatic electric field, is less than the non-electrostatic field, which is a constant. It's based on the tendency or ability to separate charges, push on charges chemically in this case, chemical forces, which is electromagnetic as well, but doesn't really matter. Okay, now what I'm showing here is an electric field that exists around here. I mean, this is connected by some path, and so the electric field exists between these 2 points, and you can think of it as existing around here as well. Now don't overly analyze this. Even though I'm showing these as the same size as this and as a vector, just think of these being really distributed along this circuit. Is very tiny electric field per length that causes the charges to keep flowing. Right? So hopefully that is enough clarity. So the non-electrostatic field is bigger than the electrostatic field, which causes positive charges then. See, this wins out over this inside the battery. So positive charges are going to flow across this way from the negative to the positive in the solution. So it's going to be shown as I non-electrostatic, which is also I electrostatic, which is just the current in the circuit. So here, this is the current that's flowing as a result of this non-electrostatic field winning out over this inside here. And that's an ongoing process, putting extra charges on there, which then move across or around this circuit, resulting in a I, we're going to call that current from the electrostatic field, pushing the charges around the circuit. Now if there's no internal resistance, if this is a perfect ideal battery, then we have the following situation. At VAB, quiet down, lady. No, I don't know what she's barking about. So VAB equals IR external. The voltage from here to here is the current times the resistance. So this current, or this current for that matter, times the resistance of the circuit. That's Ohm's law. And that is the EMF. So that's the EMF of the source. No internal resistance. The voltage that's established across these terminals. Okay. Now, if we have an internal resistance, here I'll put an external circuit here with resistance R, and we have the flow of charge moving around just like we talked about, and the non-electrostatic E field, and here we have the electrostatic E field, and I'm putting this resistor symbol in here to denote that this battery can be modeled as having a resistor internal to the battery. Now it doesn't really exist as a resistor, but effectively this is how it functions, as though there's a resistance inside. We'll call it R internal. And there's a current that flows through that. So think of this again as being a model where the charges that flow encounter resistance to their motion, to their flow, moving from B to A. So we have a non-zero internal resistance, the current flowing through it. If we have a current flowing through this resistor, then it's plus here and minus over here. So it's plus to minus, which reduces how positive this is with respect to this side. So it will decrease VAB. VAB goes down. So VAB is now the EMF, like it was before, reduced by the current times the resistance, this internal resistor. Okay, hopefully that makes sense to you at this point. We'll continue to clarify how voltages drop across resistors. Higher energy on this side, lower energy on this side. As the charges move through this resistor, they lose energy. So that's why that makes sense. So VAB is subsequently reduced as well. That's really a key relationship in our discussion here. And this is IR, basically the current, the external current times the resistance of this circuit. That's the potential across VAB. So it's been modified from what we had before. The VAB was just the EMF. So now we can factor out the I in the above. I times big R plus little r is EMF. And we have I, the current flow, is equal to the EMF, which is a characteristic property of the battery, over the combined resistance R plus R. We have this resistor and the external resistor both conspiring to reduce the current. And you can see there's reduction because they're both in the denominator. Now we've considered the conditions for an open circuit, which are pretty tranquil. Let's now consider a short circuit, which simply means in the external circuit we have a path that has zero resistance. So consider this to be a zero resistance path or a short circuit, shorting the circuit out. Now we have the non-electrostatic E field, characteristic property, and from charges here we have an electrostatic E field as shown, and short circuit current, which is passing through this internal resistor. All right, so that's also going through the external circuit of zero resistance. Notice I'm not putting an E field in here. The fact is the electric field between these 2 points is enough to produce a current that's equal to the current that's in here. In fact, it has to be the same as this current inside the battery because there's nowhere else for it to go. But trying to be technical, the electric field on a short circuit, if it's zero resistance, would actually be zero. So we never quite achieve that unless we have a superconductor. Now since the external resistance is zero, it's easy to see then that with this resistance zero, the only resistance left in the circuit is the internal resistance. So what's the size of this short circuit current? It's simply the EMF produced by this non-electrostatic E field divided by the resistance of the circuit, which is now the little r, or R internal. So that is the short circuit current. And what's VAB? Well, any charge that goes to A and is separated from B immediately zips around here without any resistance. So all of it does it. So you should know what it ought to be. Let's see if it works out mathematically. EMF minus IR, the EMF across here, minus the potential difference across this internal resistance. Well, that potential difference is EMF over R internal. And so those all cancel and we get zero. So there is no VAB. It drops to zero. Okay, so that means the electrostatic E field is zero. Really, it makes sense because there's just no charges, no charge separation. As soon as those charges get moved by the non-electrostatic E field, they immediately all get depleted because there's no resistance to their flow around the circuit. So what's the maximum possible current from a source where the terminal voltage is zero? If you have the terminal voltage zero, that's the condition of a short circuit, which is the current from a short circuit producing no voltage on the output, and that's what we just found, the EMF over the internal resistance. So now, the open circuit circumstance, VAB is equal to EMF. But if we have an internal resistance, we can solve for that internal resistance. It's EMF over the short circuit current. So these two kind of opposite extremes specify the source of EMF. It describes the open terminal voltage, nothing hooked to the thing. Put a voltmeter across there, that is actually the EMF as well. And you can figure out the internal resistance by taking that EMF and dividing it by the current you get when you just connect a perfect conductor around there and read the current. You now can see why a source cannot produce infinite current, because it would have an infinite potential drop across here, and that's impossible. We only have available to us the potential difference produced by this non-electrostatic electric field across that distance. All right, and now one last thing is the conditions for charging a battery. So here we have a battery, and we're going to put a generator instead of a resistor. Now we have a generator in the circuit, which actually is going to produce a bigger potential difference than the EMF of the battery. So what's going to happen is we have the non-electrostatic E field, but this generator is going to produce an electric field that's big enough that it's bigger than the non-electrostatic field, which produces a current through that internal resistance in the other direction. So we're going to call that I of charging, the charging current. So the charging source must equal the EMF, but more than that, a little added potential difference, and that additional potential difference causes a flow through that internal resistance in the opposite direction. And this charge flow, what ultimately happens is it reverses the chemical reaction, increasing the chemical potential energy that's in the battery, and that's how you recharge a battery. And so we have that VAB. Well, it's this voltage from the non-electrostatic E field, which is the VAB of the open circuit, but now we have plus to minus here, so it increases this VAB even more by the quantity charging current times the internal resistance. So if you put a battery charger on a battery and look at the voltage, you will see, like for instance a car battery, approximately 13 volts sitting there by itself. You put the generator on, or the battery charger, and you'll see it go up to, the terminal voltage go to 14 or even 15, depending on how hard the battery is being charged.